Hello and welcome to this session on time series forecasting. In this video, we are going to talk about what time series forecasting is. So this is what we are going to cover in this video. First of all, why time series? And then we'll talk about what exactly is time series data. And then what are the components of a time series data, like for example, the trend, seasonality, and so on. And then we will explain what each of these components are. We will also talk about when we should not use time series analysis, and we will then explain what is stationary data in terms of time series, what is the significance of stationary data, and typically time series data is not stationary, so how to make time series data stationary. And then we will take you through an example of a car sales data, and we will show you how to solve the time series or how to perform the time series analysis manually without using a tool. And then we will do in the second part, we will actually use R and we will do the same thing once again in R. Okay, so without any further delay, let's get started. And so why exactly do we need to do time series analysis? Typically, we would like to predict something in the future, and it could be stock prices, it could be the sales, or anything that needs to be predicted into the future. That is when we use time series analysis. So it is, as the name suggests, it is forecasting. And typically when we say predict, it need not be into the future. In machine learning and data analysis, when we talk about predicting, we are not necessarily talking about the future. But in time series analysis, we typically predict the future. So we have some past data and we want to predict the future. That is when we perform time series analysis. So what are some of the examples? It could be daily stock price, the shares as we talk about, or it could be the interest rates, weekly interest rates, or sales figures of a company. So these are some of the examples where we use time series data. We have historical data, which is dependent on time. And then based on that, we create a model to predict the future. So what exactly is time series? So time series data has time as one of the components, as the name suggests. So in this example, let's say this is the stock price data and one of the components. So there are two columns here. Column B is price and column A is basically the time information. In this case, the time is a day. So that primarily the closing price of a particular stock has been recorded on a daily basis. So this is the time series data and the time interval is obviously a day. Time series or time intervals can be daily, weekly, hourly, or even sometimes there is something like a sensor data. It could be every few milliseconds or microseconds as well. So the size of the time intervals can vary, but they are fixed. So if I'm saying that it is daily data, then the interval is fixed as daily. If I'm saying this data is an hourly data, then it is the data is captured every hour and so on. So the time intervals are fixed. The interval itself you can decide based on what kind of data we are capturing. So this is a graphical representation. The previous one here we saw the tabular representation, and this is how to plot the data. So on the y-axis is, let's say, the price or the stock price, and x-axis is the time. So against time, if you plot it, this is how a time series graph would look. So as the name suggests, what is time series data? Time series data is basically a sequence of data that is recorded over a specific intervals of time and based on the past values. So if we want to do an analysis of time series past data, we try to forecast a future. And again, as the name suggests, it is time series data, which means that it is time dependent. So time is one of the components of this data. Time series data consists of primarily four components. One is the trend, then we have the seasonality, then cyclicity, and then last but not least, irregularity or the random component. Sometimes it is also referred to as the random component. So let's see what each of these components are. So what is trend? Trend is overall change or the pattern of the data, which means that the data may be, let me just pull up a pen and show you. So let's say you have a data set somewhat like this, a time series data set somewhat like this. All right. So what is the overall trend? There is an overall trend which is upward trend, as we call it here, right? So it is not like it is continuously increasing. There are times when it is dipping, then there are times when it is increasing, then it is decreasing, and so on. But overall, over a period of time, from the time we start recording to the time we end, there is a trend, right? There is an upward trend in this case. So the trend need not always be upwards. There could be a downward trend as well. So for example, here there is a downward trend, right? So this is basically what is a trend. Overall, whether the data is increasing or decreasing. All right, then we have the next component, which is seasonality. What is seasonality? Seasonality, as the name suggests once again, changes over a period of time and periodic changes, right? So there is a certain pattern. Let's take the sales of warm clothes, for example. So if we plot it along the months, so let's say January, February, March, April, May, June, July, and then let's say it goes up to December. Okay, so this is our December, a D. I will just mark it as D. And then you again have Jan, Feb, March, and then you get another December. Okay, and just for simplicity, let's mark these as Decembers as the end of the year, and then one more December. Okay, so what will happen if you're talking about warm clothes, what happens? The sales of warm clothes will increase probably around December when it is cold, and then they will come down. And then again around December, again they will increase, and then the sales will come down. And then there will be again an increase, and then they will come down. And then again an increase, and then they will come down. Let's say this is the sales pattern. So you see here there is a trend as well. There is an upward trend, right? The sales are increasing over, let's say these are multiple years. This is for year 1, this is for year 2, this is for year 3, and so on. So for multiple years, overall the trend, there is an upward trend. The sales are increasing, but it is not a continuous increase, right? So there is a certain pattern. So what is happening? What is the pattern? Every December, the sales are increasing or they are peaking for that particular year, right? Then there is a new year. Again, when December approaches, the sales are increasing. Again, when December approaches, the sales are increasing, and so on and so forth. So this is known as seasonality. So there is a certain fluctuation which is periodic in nature. So this is known as seasonality. Then cyclicity. What is cyclicity? Now, cyclicity is somewhat similar to seasonality, but here the duration between two cycles is much longer. So seasonality typically is referred to as an annual kind of a sequence. Like for example, we saw here. So it is pretty much like every year in the month of December, the sales are increasing. However, cyclicity, what happens is, first of all, the duration is pretty much not fixed, and the duration or the gap length of time between two cycles can be much longer. So recession is an example. So we had, let's say, recession in 2001 or 2002 perhaps, and then we had one in 2008, and then we had probably in 2012, and so on and so forth. So it is not like every year this happens probably. So there is usually when we say recession, there is a slump, and then it recovers, and then there is a slump, and then it recovers, and probably there is another bigger slump, and so on, right? So you see here, this is similar to seasonality, but first of all, this length is much more than a year, right? That is number one. And it is not fixed as well. It is not like every 4 years or every 6 years. That duration is not fixed. So the duration can vary. At the same time, the gap between two cycles is much longer compared to seasonality. All right. So then what is irregularity? Irregularity is like the random component of the time series data. So there is like, you have part which is the trend, which tells whether the overall it is increasing or decreasing. Then you have cyclicity and seasonality, which is like kind of a specific pattern, right? Then there is a cyclicity, which is again a pattern, but at much longer intervals. Plus there is a random component, so which cannot be accounted for very easily, right? So there will be a random component which can be really random, as the name suggests, right? So that is the irregularity component. So these are the various components of time series data. Yes, there are conditions where we cannot use time series analysis, right? So can we do time series analysis with any kind of data? No, not really. So what are the situations where we cannot do time series analysis? So there will be some data which is collected over a period of time, but it's really not changing. So it will not make sense to perform any time series analysis over it, right? For example, like this one. So if we take X as the time and Y as the value of whatever the output we are talking about, and if the Y value is constant, there is really no analysis that you can do. Leave alone time series analysis, right? So that is one. Another possibility is, yes, there is a change, but it is changing as per a very fixed function like a sine wave or a cos wave. Again, time series analysis will not make sense in this kind of a situation because there is a definite pattern here, there is a definite function that the data is following. So it will not make sense to do a time series analysis. Now, before performing any time series analysis, the data has to be stationary. And typically, time series data is not stationary. So in which case, you need to make the data stationary before we apply any models like Arima model or any of these, right? So what exactly is stationary data? And what is meant by stationary data? Let us take a look. First of all, what is non-stationary data, time series data? If you recall from one of my earlier slides, we said that time series data has the following 4 components: the trend, seasonality, cyclicity, and random component or irregularity, right? So if these components are present in time series data, it is non-stationary, which means that typically these components will be present. Therefore, most of the time, a time series data that is collected raw data is non-stationary data. So it has to be changed to stationary data before we apply any of these algorithms. All right, so a non-stationary time series data would look like this, which means, like for example here, there is an upward trend, the seasonality component is there, and also the random component and so on. So if the data is not stationary, then the time series forecasting will be affected. So you cannot really perform a time series forecasting on a non-stationary data. So how do we differentiate between a stationary and a non-stationary time series data? Typically or technically, one is, of course, you can do it visually. In non-stationary data, the data will be more flattish. The seasonality will, of course, be there, but the trend will not be there. So the data may, if we plot that, it may appear somewhat like this, right? It's a horizontal line. Along the horizontal line, you will see. Compared to the original data, there was an upward trend, so it was changing somewhat like this, right? So this is non-stationary data, and this is how a stationary data would look visually. What does this mean? Technically, this means that the stationarity of the data depends on a few things: the mean, the variance, and the covariance. So these are the 3 components on which the stationarity of the data depends. So let's take a look at what each of these are. For stationary data, the mean should not be a function of time, which means that the mean should pretty much remain constant over a period of time, right? So there shouldn't be any change. So this is how the stationary data would look. And this is how a non-stationary data would look. I've shown in the previous slide as well. So here, the mean is increasing. That means there is an upward trend. Okay, so that is one part of it. And then the variance of the series should not be also a function of time. So the variance also should be pretty much common, or should be constant rather. So this is if we visually take a look, this is how time series stationary data would look, where the variance is not changing. Here the variance is changing, therefore this is non-stationary, and we cannot apply time series forecasting on this kind of data. Similarly, the covariance, which is basically of the ith term and the I plus mth term, should not be a function of time as well. So covariance is nothing but not only the variance at the ith term, but the relation between the variance at the ith term and the I plus mth or the I plus nth term. So once again, visually this is how it would look if the covariance is also changing with respect to time. So these are all three components should be pretty much constant. And that is when you have stationary data, and in order to perform time series analysis, the data should be stationary. Okay, so let's take a look at the concept of moving average, or the method of moving average, and let's see how it works. We'll do simple calculations. So let's say this is our sample data. We have the data for 3 months, January, February, March. The sales in thousands rather, not hundreds, thousands of dollars is given here, and now we want to find the moving average. So how do we find the moving average? We call it as moving average 3. So moving average 3 is nothing but you take 3 of the values or the readings, add them up and divide by 3. Basically the way we take a mean or average of the 3 values. So that is as simple as that. So that's the average first of all. So what is moving average? Moving average is if you now have a series of data, you keep taking the 3 values, the next 3 values, and then you take the average of that, and then the next 3 values, and so on and so forth. So that is how you take the moving average. So let's take a little more detailed example of car sales. So this is how we have the car sales data for the entire year, let's say. So rather for 4 years. So year 1 we have for each quarter 1, 2, 3, 4, and then year 2, quarter 1, 2, 3, 4, and so on and so forth. So this is how we have sales data of a particular car, let's say, or a showroom. And we want to forecast for year 5. So we have the data for 4 years. We now want to forecast for the 5th year. Let's see how it works. First of all, if we plot the data as it is taken, the raw data, this is how it would look. And what do you think? Is it stationary? No, right? Because there is a trend, upward trend. So this is not a stationary data. So we need to, later we will see how to make it stationary. But to start with, just an example. We will not worry about it for now. We will just go ahead and manually do the forecasting using what is known as moving average method. Okay, so we are not applying any algorithm or anything like that. In the next video, we will see how to apply an algorithm, how to make it stationary, and so on. All right, so here we see that all the 3 or 4 components that we talked about are there. There is a trend, there is a seasonality, and then of course there is some random component as well. Cyclicity may not be, it is possible that cyclicity is not applicable in all the situations. For sales especially, there may not be, or unless you're taking a sales for maybe 20-30 years, cyclicity may not come into play. So we will just consider primarily the trend, seasonality, and irregularity, right? So random, it is also known as random irregularity, right? So we were calling the random or irregularity component. So these are the 3 main components typically in this case we will talk about. So this is the trend component, and we will see how to do these calculations. So let's take a look, redraw the table including the time code. We will add another column which is the time code, and this is the column. And we'll just number it like 1, 2, 3, 4 up to 16. The rest of the data remains the same. Okay, so we will do the calculations now. Now let us do the moving average calculations or MA4 as we call it for each year. So we take all the 4 quarters and we take an average of that. So if we add up these 4 values and divide by 4, you get the moving average of 3.4. So we start by putting the value here. So that will be for the 3rd quarter, let's say 1, 2, 3, the 3rd quarter. Then we will go on to the next one. So we take the next 4 values as you see here and take the average of that, which is the moving average for the next quarter, and so on and so forth. Now, if we just do the moving average, it is not centered. So what we do is we basically add one more column and we calculate the centered moving average as shown here. So here what we do is we take the average of 2 values and then just adding these values here. So for example, the first value for the 3rd quarter is actually the average of the 3rd and the 4th quarter. So we have 3.5. Now it gets centered. So similarly, the next value would be 3.6 plus 3.9 divided by 2, so which is 3.7, and so on and so forth. Okay, so that is the centered moving average. This is done primarily to smoothen the data so that there are not too many rough edges. So that is what we do here. So if we visualize this data now, this is how it looks. Right, so if we take the centered moving average, as you can see, there is a gradual increase. If this was not the case, if we had not centered it, the changes would have been much sharper. So that is basically the smoothing that we are talking about. Now let's go and do the forecast for the 5th year. So in order to do the forecast, what we will do is we will take the centered moving average as our baseline and then start doing a few more calculations that are required in order to come up with the prediction. So what we are going to do is we are going to use this multiplicity or multiplicative model in this case, and this is how it looks. So we take the product of seasonality and the trend and the irregularity components, and we just multiply that. And in order to get that, this product of these two, we have basically the actual value divided by CMA. YT value divided by CMA will give you the predicted value, or YT is equal to the product of all three components. Therefore, ST into YT is equal to YT by CMA. So this is equal to YT, right? So therefore, if we want ST into YT, the product of seasonality and irregularity, it is equal to YT by CMA. So that is how we will work it out. I also have an Excel sheet of the actual data. So let me just pull that up. Alright, so this is how the data looks in Excel. As you can see here, year 1, quarter 1, 2, 3, 4, year 2, quarter 1, 2, 3, 4, and so on. And this is the sales data. And then this is the moving average. As I mentioned, this is how we calculate. And this is the centered moving average. So this is the primary component that we will start working with. And then we will calculate, since we want the product of ST into YT, that is equal to YT by CMA. So if you see, these values are nothing but the YT value divided by CMA. So in this case, it is 4 by 3.5, which is 1.14. Similarly, 4.5 by 3.7, 1.22, and so on and so forth. So we have the product ST into YT, and then the next step is to calculate the average of respective quarters. So that is what we are doing here, average of respective quarters, and then we need to calculate the deseasonalized values. So in order to get deseasonalized value, we need to divide YT by ST that was calculated. So for example, here it is 2.8 by 0.9. So we got the deseasonalized value here, and then we get the trend, and then we get the predicted values. So in order to get the predicted value, which is basically we predict the values for known values as well. Like for example, year 1, quarter 1, we know the value, but now that we have our model, we predict ourselves and see how close it is. So we predicted as 2.89, whereas the actual value is 2.8. Then we have 2.59, the actual value is 2.1, and so on, just to see how our model works, and then continue that into the 5th year, because for 5th year we don't have a reference value. Okay, and if we plot this, we will come to know how well our calculations are, how well our manual model. In this case, we did not really use a model, but we did on our own manually. So it will tell us the trend. So for example, the predicted value is this gray color here, and you can see that it is actually pretty much following the actual value, which is the blue color. Right? And the gray color is the predicted value. So wherever we know the values up to year 4, we can see that our predicted values are following or pretty much very close to the actual values. And then from here onwards, when the year 5 starts, the blue color line is not there because we don't have the actual values, only the predicted value. So we can see that since it was following the trend pretty much for the last 4 years, we can safely assume that it has understood the pattern and it is predicting correctly for the next 1 year, the next 4 quarters, right? So that is what we are doing here. So these 4 quarters, we did not have actual data, but we have the predicted values. So let's go back and see how this is working in this using the slides. So this is, we already saw this part, and I think it was easier to see in the Excel sheet. So we calculated the ST, IT, the product of ST and IT using the formula like here, YT by CMA, we got that, and then we got ST, which is basically YT. So this is average of the first quarters for all the 4 years. And similarly, this is the average of the second quarter for all the 4 years, and so on. So these values are repeating. They are calculated only once. They get repeated, as you can see here. And then we get the deseasonalized data, and that is basically YT by ST. So we calculated ST here, and we have YT. So YT by ST will give you the deseasonalized data. And we have got rid of the seasonal and the irregular components so far. Now what we are left with is the trend. And before we start the time series forecasting or time series analysis, as I mentioned earlier, we need to completely get rid of the non-stationary components. So we are still left with the trend component. So now let us also remove the trend component. In order to do that, we have to we have to calculate the intercept and slope of the data, because that is required to calculate the trend. And how are we going to do that? We will actually use what is known as a regression tool or analytics tool that is available in Excel. So you remember we have our data in Excel. So let me take you to the Excel, and here we need to calculate the intercept and the slope. In order to do that, we have to use the regression mechanism, and in order to use the regression mechanism, we have to use the analytics tool that comes with Excel. So how do you activate this tool? So this is how you would need to activate the tool. From Excel, you need to go to Options, and in Options there will be Add-ins, and in Add-ins you will have Analysis Toolpack, and you select this and you just say Go. It will open up a box like this. You say Analysis Toolpack and you say OK. And now when you come back into the regular view of Excel, in the Data tab, you will see Data Analysis activated. So you need to go to File, Options, and Add-ins, and then Analysis Toolpack. Typically, since I've already added it, it is coming at the top, but it would come under Inactive Application Add-ins. So when you're doing it for the first time. So don't use VBA, you just say Analysis Toolpack. There are two options, one with VBA like this one and one without VBA. So just use the one without VBA. And then instead of just saying OK, just take care that you click on this Go and not just OK. So you say Go, then it will give you these options. Only then you select just the Analysis Toolpack and then you say OK. Alright, so and then when you come back to the main view, you click on Data. Okay, so this is your normal home view perhaps. So you need to come to Data, and here is where you will see data analysis available to you. And then if you click on that, there are a bunch of possibilities of what kind of data analysis you want to do. If there are options are given. Right now we just want to do regression because we want to find the slope and the intercept. So select regression and you say OK. And you will get these options for input Y range and input X range. Input Y range is the value YT. So you just select this and you can select up to here and press enter. And input X range, you can, for now, you start with the baseline, or you can also start with the deseasoned values. So you can just click on these and say OK. I have already calculated it. So these are the intercept and the coefficients that we are getting for these values. And we will actually use that to calculate our trend here, right? So which is in the J column. So our trend is equal to intercept plus slope into the time code. So the intercept is out here, as we can see in our slide as well. So if you see here, this is our intercept, and the lower value is the slope. So we have calculated here and it's shown in the slides as well. So intercept, so the formula is shown here. So our trend is equal to intercept plus slope into time code. Time code is nothing but this one, T, column A, 1, 2, 3, 4. Okay. So that's how you calculate the trend, and that's how you use the data analysis tool from Excel. Using these two, we calculate the predicted values. And using this formula, which is basically trend is equal to intercept plus slope into time code. And then we can go and plot it, see how it is looking. And therefore, so we see here that the predicted values are pretty close to the actual values. And therefore, we can safely assume that our calculations, which are like our manual model, is working. And hence, we go ahead and predict for the 5th year. So till 4 years, we know the actual value as well, so we can compare how our model is performing. And for the 5th year, we don't have reference values, so we can use our equations to calculate the values or predict the values for the 5th year, and we can go ahead and safely calculate those values. And when we plot for the 5th year as well, the predicted values, we see that they are pretty much, they captured the pattern, and we can safely assume that the predictions are fairly accurate, as we can also see from the graph in the Excel sheet that we have already seen. Okay, so let's go and plot it. So this is how the plot looks. This is the CMA, or the centered moving average, the green color, and then the blue color is the actual data, red color is the predicted value, predicted by our handcrafted model. Okay, so remember, we did not use any regular forecasting model or any tool. We have done this manually, and the actual tool will be used in the next video. This is just to give you an idea about how behind the scenes or under the hood, how forecasting works, or time series analysis, how it is performed. Okay, so it looks like it has captured the trend properly. So up to here is the known reference, we have reference, and from here onwards is purely predicted. And as I mentioned earlier, we can safely assume that the values are accurate and predicted properly for the 5th year. So let's go ahead and implement a time series forecast in R. First of all, we will be using the Arima model to do the forecast of this time series data. So let us try to understand what is Arima model. So Arima is actually an acronym. It stands for Autoregressive Integrated Moving Average. So that is what is Arima model. And it is specified by 3 parameters, which is P, D, and Q. P stands for autoregressive. So let me just mark this. So there are 3 components here: autoregressive, integrated, moving average. Okay. So these 3 parameters correspond to those 3 components. So the P stands for autoregressive, D for integrated, and Q for moving average. So let us see what exactly this is. So these 3 factors are: P is the number of autoregressive terms, or AR, we will see that in a little bit, and D is how many levels of differences that we need to do, or differentiation we need to do, and Q is the number of lagged forecast errors. So we'll see what exactly each of these are. So AR is the number of autoregressive terms, and which is basically denoted by the P, and then we have D, which is for the number of times it has to be differentiated, and then we have Q, which is for the moving average. So what exactly AR terms? So in terms of the regression model, autoregressive components refer to the prior values of the current value. Well, what we mean by that is, here when we talk about time series data, focus on the fact that there is regression. So what exactly happens in regression? We try to do something like, if it is simple linear regression, we do some equation like y is equal to mx plus c, where there are 2 variables. One is the dependent variable, and then there is an independent variable. Let me just complete this equation as well, mx plus c. Right? So this is a normal regression curve, or a simple regression curve. Now here we are talking about autoregression or autoregressive. So autoregressive, as the name suggests, is regression of itself. So which means that here you have only one variable, which is your maybe the cost of the flights or whatever it is, right? And the other variable is basically time dependent, and therefore the value at any given time, and that we will denote as yt, for example. So there is no x here, there is only one variable, and which is y, and we say yt, which is basically the predicted value at a time interval t, for example, is dependent on the previous value. So for example, there may be a1 and then yt minus 1, and then there will be like plus a2 and plus a2 and yt minus 2 and all right, and then plus a3 into yt minus 3. Correct? So basically here what we are saying is there's only one variable here, but there is a regression component. So we are doing a regression on itself. So that's how the term auto regression comes into play. So only thing is that it is dependent on the previous time values. So there is a lag, let's say. This is the first lag, second lag, third lag, and so on. So the current value, which is yt, is dependent on the previous time lag values. So that is what is auto regression component. So this is what is shown here. For example, in this case, instead of y, we are calling it as x. So that's the same. And this is represented by some equation of that sort, depending on how many lags we take. So that is the AR component. And the term P is basically determines how many lags we are considering. So that's the term P for. Now, what is D? D is the degree of differencing. So here differencing is like for the non-seasonal differences, right? So for example, if you take the values like this, which are given for 5, 4, 6, and so on and so forth, if you take the differencing of one after another, like for example, 5 minus 4 or 4 minus 5, the next value with the previous value. So 4 minus 5. So this is known as the first order differencing. So the result is minus 1. Similarly, 6 minus 4 is 2. 7 minus 6 is 1. So this is first order differencing. And here we call it as D is equal to 1. Okay. And same way we can have second order, third order, and so on. Then the last one is Q. Q is the actually why we call it moving average, but in reality it is actually the error of the model. So we also sometimes represent as ET. Alright, so now Arima model works on the assumption that the data is stationary, which means that the trend and seasonality of the data has been removed. That is correct. Okay. So this we have discussed in the first part, what exactly is stationary data and how do we remove the non-stationary part of it. Now, in order to test whether the data is stationary or not, there are two important components that are considered. One is the autocorrelation function and the other is the partial autocorrelation function. So this is referred to as ACF and PACF. Correct. So what is autocorrelation and what is the definition? Autocorrelation is basically the similarity between values of a same variable across observations, as the name suggests. Now, how do we actually find the autocorrelation function, the value, right? So this is basically done by plotting, and autocorrelation function also tells you how correlated points are with each other based on how many time steps they are separated by and so on. That is basically the time lag that we were talking about. And it is also used to determine how past and future data points are related. And the value of the autocorrelation function can vary from -1 to 1. So if we plot, this is how it would look. Autocorrelation function would look somewhat like this. And there is actually a readily available function in R. So you will see that and you can use that to plot your autocorrelation function. Okay. So that is ACF, and we will see that in our RStudio in a little bit. And similarly, you have partial autocorrelation function. So partial autocorrelation function is the degree of association between two variables while adjusting the effect of one or more additional variables. So this again can be measured and it can also be plotted, and its value once again can go from -1 to 1, and it gives the partial correlation of time series with its own lagged values. So lag again we have discussed in the previous couple of slides. This is how a PACF plot would look in RStudio. We will see that as well, and once we get into the RStudio. And with that, let's get into RStudio and take a look at our use case. Before we go into the code, let's just quickly understand what exactly is the objective of this use case. So we are going to predict some values or forecast some values, and we have the data of the airline ticket sales of the previous years, and now we will try to find or predict or forecast the values for the future years. All right. So we will basically identify the time series components like trend, seasonality, and random behavior. We will actually visualize this in RStudio, and then we will actually forecast the values based on the past values or history data, historical data. So these are the steps that we follow. We will see in RStudio in a little bit. Just quickly, let's go through what are the steps. We load the data, and it is a time series data. We try to find out what class it belongs to. The data is actually air passengers data that is already comes preloaded with RStudio. So we will be using that, and we can take a look at the data, and then what is the starting point, what is the end point. So these are all functions that are readily available we'll be using, and then what is the frequency. It's basically frequency is 12, which is like yearly data, right? So every month the data has been collected. So for each year it is 12. And then we can check for any missing values if there are any. And then we can take a look at summary of the data. This is what we do in exploratory data analysis. And then we can plot the data, visualize the data, how it is looking, and we will see how the data has some trend, seasonality, and so on and so forth. All right, then we can take a look at the cycle of the data using the cycle function, and we can see that it is every month. That's the cycle. End of every 12 months, a new cycle begins. So each month of the year is the data is available. Then we can do box plots to see for each month how the data is varying over the various 10 or 12 years that we will be looking at this data. And from exploratory data analysis, we can identify that there is a trend, there is a seasonality component, and how the seasonality component varies also we can see from the box plots. And we can decompose the data. We can use the decompose function rather to see the various components like the seasonality, trend, and the irregularity part. Okay, so we will see all of this in RStudio. This is how they will look. This is the once you decompose, and this is how you can visualize the data. This is the actual data, and this is the trend. As you can see, it's going upwards. This is the seasonal component, and this is your random or irregularity, right? So we call it irregularity, or we can also call it random, as you can see here. Yes, so the data must have a constant variance and mean, which means that it is stationary before we start any analysis, time series analysis. And so basically, yeah, if it is stationary, only then it is easy to model the data, perform time series analysis. So we can then go ahead and fit the model. As we discussed earlier, we'll be using Arima model. There are some techniques to find out what should be the parameters. So we will see that when we go into RStudio. So the AutoArima function basically tells us what should be the parameters, right? So these parameters are the P, D, and Q that we talked about. That's what is being shown here. So if we use AutoArima, it will basically take all possible values of this P, D, Q, these parameters, and it will find out what is the best value, and then it will recommend. So that is the advantage of using AutoArima. All right. So like in this case, it will tell us if we use this parameter trace, we set the parameter trace is equal to true, then it will basically tell us what is the value of this AIC, which has to be minimum. So the lower the value, the better. So for each of these combinations of P, D, and Q, it will give us the values here, and then it will recommend to us which is the best model. Okay. Because whichever has the lowest value of this AIC, it will recommend that as our best PDQ values. So once we have that, we can see that we can potentially get a model or the equation. Model is nothing but the equation, and based on the parameters that we get. And we can do some diagnostics. We can do some plotting to see whether there is a plot for the residuals, so which shows the stationarity. And then we can also take a look at the ACF and PACF. We can plot the ACF and PACF, and then we can do some forecasting for the future years. So in this case, we have up to 1960, and then we can see how we can forecast for the next 10 years, which is 1970, up to 1970. And once we have done this, can we validate this model? Yes, definitely we can validate this model. And to validate the findings, we use junk box test, and this is how you just call box.test, and then you pass these parameters, and you will get the values that will be returned, which will tell us whether how accurate this model is, how accurate the predictions are. So the values of P are quite insignificant in this case. We will see that, and that also indicates that our model is free of autocorrelation, and that will basically be it. So let's go back and into our RStudio and go through these steps in real time. So we have to import this library. Forecast package is not installed. You have to go here and install the forecast package. Okay, so that's the easy way to install rather than to click on this install. I will not do it now because I've already installed. So the first time, that's only one time. Then after that, you just have to load it into memory and then keep going. So we will load this data called air passengers. So by calling this data method, and if you see the data air passengers is loaded here, and if we check for the class, it is a time series data, TS data. So we can check for the dates. We can also view the data in a little bit, and the start date is 1949 and January, and our end date is 1960 December, and the frequency is 12, which is like collected monthly. So that is the frequency, which is 12 here, and then we check if there are any missing values. There are no missing values, and then we take a look at the summary of the data. This is all exploratory data analysis, and then if you just display the data, this is how it looks. And then we need to decompose this data. So we will kind of store this in an object TS data and then use that to decompose and store the new values. Let me just clear this for now. And if we decompose, basically, as we have seen in the slides, decomposing is breaking it into the trend, seasonality, and the irregular or random components. Then you can go ahead and plot it. So when you plot it, you can see here, let me zoom this. This is our original plot, or observed value as it is known as. Then we have decomposed the three parts, which is basically the trend. As you can see, there is an upward trend. Then the seasonal component. So this is some regularly occurring pattern. And then there is a random value, which is basically you cannot really give any equation or function or anything like that. So that's what this plotting has done. And then you can actually plot them individually as well. So these are the individual plots for the trend, for the seasonal component, and the random component. All right. So now let's take a look at the original data and see how the trend is in a way. So if we do this linear regression line, it will show that it is going upwards. And we can also take a look at the cycle that are there, which is nothing but we have a frequency of 12, right? So the cycles will display that it is January, February to December, and then back to January, February, and so on and so forth. And if we do box plots for the monthly data, you will see that for each of the months, right? And over the 10 years that the data that we have, we will see that there is a certain pattern, right? This is also in a way to find the seasonality component. So while January, February sales are relatively low, around July, August, the sales pick up. So especially in July, I think the sales are the highest. And this seems to be happening pretty much every year, right? So this is every year in July, there seems to be a peak in the sales, and then it goes down and slightly higher in December and so on. So that is again part of our exploratory data analysis. And once again, let's just plot the data. Now, as I said, in order to fit into an Arima model, we need the values of P, D, and Q. Now, one way of doing it is, there are multiple ways actually of doing it. The earlier method of doing it was you draw the autocorrelation function plot and then partial autocorrelation function plot and then observe that and where does this change and then identify what should be the values of P and Q and so on. Now, R really has a very beautiful method which we can use to avoid all that manual process that we used to do earlier. So what R will do is, there is a method called AutoArima, and if we just call this AutoArima method, and it will basically go and test the Arima model for all possible values of these parameters P, D, Q, and then it will suggest to you what should be the best model, and it will return that best model with the right values of P, D, and Q. So we as data scientists don't have to do any manual, trial and error kind of stuff. Okay, so we got the model now, and this is the model. It has PDQ values are 2, 1, 1 PDQ, and this is the seasonal part of it, so we can ignore it for now. And so if we want to actually understand how this has returned these values 2, 1, 1 as the best one, there is another functionality or feature where we can use this trace function or trace parameter. So if you pass to AutoArima the trace parameter, what it will do is it will show you how it is doing this calculation. What is the value of the AIC? Basically, AIC is what defines the accuracy of the model. The lower, the better. Okay. So for each combination of PDQ, it will show us the value of AIC. So let's run it instead of me talking so much. Let's run this. If we run AutoArima with trace, you see here there is a red mark here. That means it is performing, it's executing this, and here we see the display, right? So it starts with certain values of PDQ, and then it finds that value is too high. So it starts with again with some 0, 1, 1, 0, and so on and so forth. And ultimately it tells us, okay, this is our best model. You see here, so it says this is our best model 2, 1, 1. Let's go back and see, did we get the same one? Yes, we got the same one when we ran without trace as well, right? Now, why is 2, 1, 1? Let us see where is 2, 1, 1. Here is our 2, 1, 1. And if you compare the values, you see that 1017 is pretty much the lowest value, and therefore it is saying this is our best model. All other values are higher. So that's how you kind of get your model. And now that you have your model, what you have to do, you need to predict the values, right? So before that, let us just do some test of these values. So for that, you install T-Series. Again, if you are doing it for the first time, you would rather use this package and install and say T-Series and install it. And then you just use this library function to load it into your memory. Alright, so now that we got our model using AutoArima, let us go ahead and forecast and also test the model and also plot the ACF and PSCF. Remember, we talked about this, but we did not really use it. We don't have to use that, but at least we will visualize it. And for some of the stuff, we may need this T-Series library. So if you are doing this for the first time, you may have to install it. And my recommendation is don't use it in the code. You go here and install T-Series. And I will not do it now because I have already installed it, but this is a preferred method. And once you install it, you just load it using this libraries function, and then you can plot your residuals, and this is how the residuals look, and you can plot your ACF and PSCF. Okay, so this is how your PSCF looks, and this is how your ACF looks. For now, there is really nothing else we need to do with ACF and PSCF. This is just to visualize how it looks. But as I mentioned earlier, we were actually using these visualizations or these graphs to identify the values of P, D, and Q. And how that was done, it's out of scope of this video, so we will leave it at that. And then we will forecast for the next 10 years. How do we forecast that? So we call forecast, and we pass the model, and we pass what is the level of accuracy that you need, which is 95%, and for how many periods, right? So basically we want for 10 years, which is like 10 into 12 time periods. So that's what we are doing here. And now we can plot the forecast value. So you see this is the original value up to I think 62 or whatever, and then it goes up to 72. This blue color is the predicted value. Let's go and zoom it up so that we can see it better. So from here onwards, we're forecasting, and you can see that it looks like our model has kind of learned the pattern, and this pattern looks very similar to what we see in the actual data. Now, how do we test our model? So we can do what is known as a box test, and we pass our model here, residuals basically, with different lags, and from those values here, the p values here, we find that they are reasonably low, the p values, which means our model is fairly accurate. With that, we come to the end of this video. I hope you enjoyed this. Thank you very much once again for joining. And if you have any comments or questions, please put it at the bottom of the video, and preferably with some contact information so that we can get back to you. And you have a great day. Thank you once again. Bye-bye.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.